Hello students, myself Amrita Roy. Today we are going to study about single phase AC circuit and resonance. Let us go through the contents. We are going to study about J operator, concept of complex impedance, that is rectangular and polar form, series AC circuits and parallel AC circuits. First one is the study of J operator. We can see from the diagram that the four quadrants are divided into 4 degrees, that is 0 degree, 90 degree, 180 degree and 270 degrees. We all know that for a complex equation, the imaginary part is always represented as root over of -1. But in terms of circuit theory, we will interpret the symbol J when placed in front of a phasor to mean advance the phase of the phasor by 90 degrees and -j to mean retard the phase by 90 degrees. So we have considered a table for each 90 degree rotation, as first 90 degree rotation will be j, that is root over of -1, that will indicate plus j, and we will consider the rotation in anti-clockwise direction as positive. So for 180 degree rotation it will be j into j, that is j square, representing -1. For another 90 degree rotation it will represent 270 degree, which is j cube, that is equals to -j. And for the last 90 degree rotation, that is 360 or 0 degree, it will represent j to the power 4, that is equals to +1. Concept of complex impedance, that is rectangular and polar form. So in rectangular form, we can express the vector in terms of its rectangular coordinates, with the horizontal axis being the real one and the vertical axis being the imaginary axis or the j component. So in polar form, these real and imaginary axes are simply represented by a angle theta. So if you convert between the rectangular and polar coordinates, we can see that converting from rectangular to polar coordinate will give the absolute value as r equals to root over of x square plus y square and the angle as theta equals to tan inverse y by x. Now if we convert from polar to rectangular coordinates, we will get the x-axis, that is x equals to r cos theta and y equals to r sin theta. So if we represent it as a triangle in the first quadrant, we can see that the x-axis is represented by x and y-axis as y and the hypotenuse as the radius or r. So it will represent x equals to r cos theta for the real part and y equals to r sin theta for the imaginary part. Left hand side, I have given the graph for the inductor and capacitor, where it will represent leading and lagging nature of the passive elements of inductor and capacitor. So in a pure resistive circuit, both the current and voltage are said to be in phase, as there is no phase difference between them. In a pure inductive circuit, the inductor current lags behind the inductor voltage by 90 degrees, and in a pure capacitive circuit, the capacitor current leads capacitor voltage by an angle of 90 degrees. First one is the series AC circuits. So the series RL circuit is given as a supply voltage VT. So and it is representing a resistance in series with supply voltage and an inductor in series with the resistor. So an RL circuit is defined as an electrical circuit consisting of passive circuit elements R and L together and driven by a voltage or current source. So let the applied current in the series RL circuit be I, and the voltage drop across R and L is given by VR equals to IR, that is R into Im sin omega t. VL equals to L di by dt, that is L into ddt of Im sin omega t. This is omega L Im cos omega t. So we will get the equation as VL equals to omega L Im sin omega t plus 90 degree. So the total voltage drop in the circuit is given by V equals to VR plus VL, and by converting the instantaneous value into peak value multiplied with the sinusoidal waveform, we will get the final equation as Vm sin omega t cos theta plus Vm cos omega t sin theta equals to Rim sin omega t plus omega L Im sin omega t cos 90 degree plus omega L Im cos omega t sin 90 degree, representing the real part as Vm sin omega t cos theta equals to Rim sin omega t, which will become 0 as since omega Im sin omega t cos 90 degree equals to 0. So Vm cos omega t sin theta will be equals to omega L Im cos omega t sin 90 degree omega L Im cos omega t. Then we finally obtain Vm cos theta equals to Rim and Vm sin theta equals to omega L Im. So Vm will be equal to root over of Rim whole square plus omega L Im whole square will be equal to Im root over of R square plus omega whole square equals to Im into Z, and theta will be equals to tan inverse omega L by R. So the impedance will be given by root over of R square plus omega whole square and angle of tan inverse of omega L by R. So in this case the voltage leads the current by an angle phi. Here we have represented it in imaginary and real axis form for the series RL circuit. The x-axis is representing R and the y-axis is representing L, and the impedance is given by RL plus j omega L in Cartesian form, and in polar form it is given by ZL e to the power j phi. So by taking modulus value, we will get ZL equals to root over of L square plus omega L whole square. So, and the phi will be given by tan inverse of omega L divided by RL. Next is the series RC circuit. A series RC circuit is shown by the figure as an R and C is connected in series with the supply voltage. Now in the given diagram, we can see V is equals to IR and VC equals to I into XC, where XC is equals to 1 by 2 pi FC. So if you write down the equations of the voltage drop across the resistor and the capacitor, we will get V by adding up the total voltage drop in the circuit, we will get V equals to IR plus V into I by j omega C, giving I into R minus j into 1 by omega C, that is equals to Iz. Now impedance Z equals to R minus j by omega C. Now if we convert it into polar form, we can represent it as root over of R square plus 1 by omega C whole square angle of minus tan inverse 1 by omega RC. Now the current is given by I equals to V by Z. We will get it by dividing the denominator with the numerator, that is V by root over of R square plus 1 by omega C whole square angle of minus tan inverse 1 by omega RC. So the final equation will be given by, for instantaneous current, I equals to Im sin omega t plus theta. By substituting the values of I, we will get Vm by root over of R square plus 1 by omega C square sin omega t plus tan inverse 1 by omega RC. So we have here drawn here the graphs. We can see here the current leads the voltage by an angle of 90 degrees for a series RC circuit. Here we have given the definitions for the power triangle, that is the impedance, reactance, power factor, active or true power, reactive power, apparent power. Now the electrical impedance is basically the measure of total opposition that a circuit or a part of a circuit presents to electric current, and impedance includes both resistance and reactance. So we can see in the diagram we have the impedance, phase angle, and the powers are represented as x-axis we have true power, on the y-axis we have reactive power, and on the hypotenuse we have the apparent power. So to get the apparent power, we need to find the reactive and the active power, and the reactive power is represented by the symbol Q, active power by symbol P, and apparent power as symbol S. Next is the parallel AC circuit. In the parallel AC circuit, we will first read about the parallel RL circuit. In parallel RL circuit, both the resistor and inductor are connected in parallel with each other, and this combination is supplied by a voltage source V in. Now if voltage in parallel circuit is same throughout the circuit as it is in parallel connection, so the current through R is not the same as it is flowing through L. So IR is in phase with V, but IL lags V by 90 degree. Now we know that IR will be equals to V by R, and IL will be equals to V by JXL, that is equals to V by J omega L. Now applying Kirchhoff's current law, we will get I equals to IR plus IL, giving us the total current will be divided across the resistance and the inductor. So V into 1 by R plus V into 1 by j omega L equals to Vy. Since it is a parallel circuit, we will get admittance. So Y will be equals to 1 by R plus 1 by j omega L equals to 1 by R minus j into 1 by omega L. Now for finding the angle, we will take inverse, that is tan inverse numerator divided by the denominator. So here the b, that is the imaginary part, is minus 1 by omega L. So we will put it in the numerator, and the denominator we will substitute by 1 by R, giving us tan inverse of minus R by omega L. So again, if I equals to IR plus IL, so we will get here I equals to root over of 1 by R whole square plus 1 by omega L whole square Vm cos omega t minus theta. Now when the resistance is relatively high, the current drawn by the resistance branch is low, and then I equals to IL. And when the resistance is relatively low, the current drawn by the inductive branch is negligible, and I equals to IR. So the phasor diagram of parallel circuit is given as shown in the diagram. Next is the parallel RC circuit. Here, the AC is applied to the parallel RC circuit, and the capacitor never reaches the final charge, and therefore it will always carry some current. So the voltage in parallel circuit must be the same throughout the circuit. The current through R is not the same as the current through C. So IR is in phase with V, but IC leads V by 90 degrees. So if we want to find out the value of current, we will write IR equals to V by R, that is across the resistance, and across the capacitor the current is IC equals to V by 1 by j omega C. Now vectorically we will get I equals to IR plus IC, which gives I equals to V into 1 by R plus V into 1 by j omega C, giving a total of V equals to G plus JB, where G is representing the conductance and B the susceptance. So the phase value, that is the angle value, will also be given by tan inverse of omega C by 1 by R, giving tan inverse omega RC. Also I will be equals to IR plus RC. So the total current value will be for parallel RC circuit root over of 1 by R whole square plus omega C square into Vm sin omega t plus theta. When the R is relatively high, the current drawn by the resistance branch is low, as you can see in the equation, and when the R is relatively low, the current drawn by the capacitive branch is low. So if R is much greater than 1 by omega C, theta will tend to 90 degrees, giving us I equals to IC, that is will be equal to omega C Vm sin omega t plus 90 degree. And if R is much less than 1 by omega C, it will give theta tends to 0, that is I will be equals to IR, and it will give us Vm by R sin omega t. Now the phasor diagram of the RC circuit is given as follows, that is the resultant value will be the actual current flowing through the circuit. We will represent the capacitor current along the y-axis, and the current through the resistor along the x-axis. Now if we see the triangle, we can see the conductance is in the x-axis, susceptance in the y-axis, and admittance is representing the hypotenuse for a parallel circuit. So the conductance is the degree to which the object conducts electricity, and it is abbreviated as G, and its unit is Siemens. Similarly, the susceptance is the complement of resistance and the complementary expression of reactance, and is called susceptance. It is equal to 1 by X and is measured in Siemens and symbolized as B. Similarly, the complementary measure representing the reciprocal of impedance, and it is called admittance. Its unit is also Siemens and is symbolized as capital Y. Thank you. In the next presentation, we will read about the series resonance and parallel resonance.